Okay, we're doing problem 2b from section 5.1. This one is asking us to find the open intervals where the function is concave up or down. So whenever you have a question about concavity, we know we're dealing with the second derivative. So we're going to need to first find that second derivative. So let's do that first. In order to find the second derivative, of course, we need to find the first derivative. So we'll do that. So this requires the rule for taking the derivative of an exponential function. If we remember how to do that, it's just copy the function first. That's really the first thing you should do when you're dealing with an exponential function. And then we also want to multiply by the derivative of that thing that's up there in the exponent. That's the chain rule. So that's minus 2x. So that's going to give us, when we simplify this, minus 4 x e to the minus x squared. Okay, so there's the first derivative. Now we need the second derivative. So that's going to be the derivative of this thing. That's going to require the product rule. So the product rule says first take the derivative of the first function, which will be minus 4. The first function is minus 4x. Its derivative is minus 4. Multiply that by the second function, and then add to that the first function multiplied by the derivative of the second function. The derivative of the second function, we had already actually found that. That's just going to be, let's just do the same thing we'd done before. Copy the function, multiply by the derivative of the thing that's up there. Okay? So let's simplify this. Let's rewrite this as minus 4 e to the minus x squared. And we'll multiply our constants together. We got a minus 4, we got a minus 2. That becomes plus 8. And then we've got an x, we've got another x, that's x squared. And then we've got our e to the minus x squared. Okay, so there's our second derivative. Let's go ahead and actually factor out an e to the x squared out of that thing. In fact, we can factor out a 4e to the x squared. Let's go ahead and factor out a negative 4e to the x squared. E to the negative x squared. And then when we do that, what are we left with when we factor that negative 4e to the negative x squared out? We'll have only 1 left there, plus 2. Actually, that'll be minus 2 because I'm factoring out a negative. Let me fix that. Remember, when we factor out a negative number, the signs change. So this should be 1 minus 2x squared. This is what we're going to be left with. Okay, so there is the that's the second derivative. What we do with this is we set this thing equal to 0, and we solve that. So we've got really two factors here, that one and that one. So what we want to do is to set them both equal to 0 and solve both of them. So this has no solution. When you've got an exponential function set equal to 0, there will be no solution. So we don't have to worry about that one. It's not going to produce any solution. So the other one is where we're going to get our solutions to this thing. Okay, so if I solve that one, I can move that 2x squared to one side. So we get 2x squared is equal to 1. Divide both sides by 2. I'm going to get x squared is equal to 1/2. So take the square root of both sides of this. I'm going to get x is equal to, and don't forget the plus or minus when you solve an equation like that, something squared, square root of 1/2. Well, the square root of 1 is 1, so we can just write this as plus or minus 1 over the square root of 2. And then when you rationalize this, rationalizing means multiplying by, well, if we're rationalizing the denominator here, multiply the top and the bottom by the same root that you see in the denominator. So that's going to give us plus or minus root 2 over 2. Okay, so we've got 2. These would then be called possible inflection points. This particular problem is not actually asking for that, but just so we're aware, these would possibly be inflection points. And the way that we can tell, again, that we really do have an inflection point is if we notice that the sign of the second derivative changes on either side of those possible inflection points. So our next step to find the intervals of concavity would be to set up our intervals. So we're going to get minus infinity up to the smaller of the two possible inflection points. And then we go from that one to the next one, and then from that last one up to infinity. Okay, so there's our intervals. And remember, we need our test values, and then our goal here is to determine the sign of the second derivative. And then based on that, we will draw our conclusions about what's happening with the concavity. Okay, so root 2 over 2, I think that's a number that's, it's less than 1. Absolute value anyway is less than 1. So let's pick x equals -1 for our critical number, or for our test value there. Let's pick 0 for our test value here, and let's pick 1 for our test value here. So what we want to do is take these test values and plug them into the second derivative. So let's take a look at this right here. This is our second derivative factored. That'll be a good one to use. So if I plug in -1 here, notice what happens. -1 plugged in there, squaring it gives us +1, so I'm going to have 1 minus 2. That's going to be a negative number right there. When I plug -1 in here, it doesn't matter what that is. This is always this e to the negative x squared. That's always going to be positive. But since we've got a -4 there, that makes this term also negative. So I've got a negative term here, and I've got a negative term here. So the second derivative is positive there. When I plug in 0, notice what happens now. I've got a positive number here, 1 minus 0, and then here I've got e to the 0 power. E to the 0 power is 1, so that means this whole term is going to be negative. So I've got a negative times a positive, that's negative. And then when I plug in 1, I'm going to get the same thing that I got when I plugged in -1, because both of those x's are squared. So that's going to be positive. So my conclusion here is that the function is concave up on this first interval, and then it's concave down on the second interval, and then it's concave up on the third interval. And again, since this problem is only asking us to determine the intervals where the function is concave up or down, we've done that based on the table. Okay, so if we were further asked to find inflection points, we would now know that these actually are inflection points because concavity did change. Okay, but we're not doing that in this problem, so we're finished.